So what about inverse secant? That one looks a little weird. Where does that extra absolute value of x come from? Okay, so you can start, this the usual ways. And one of the things I like about these derivations, so again, you don't have to know the derivations, you have to know the results. But what's really good is to see what a great use of how everything, that we're doing with calculus can sort of combine together to produce new results. So it's a good way to look at how the things you've already learned work. So this is a good example. Like, we know this derivative of secant is secant tangent. Okay, but what does that mean? The derivative of secant x is secant x tangent x. So the derivative of secant y is secant y tangent y. All right, so do we need a dy dx for each of those different functions? And the answer is no, because there's only one inside function here. So the inside function y stayed the same, and then we just have a dy dx that is the derivative of the inside function. It's the only inside function that there is. Okay, and then we got 1 on this side. So then the result of that is your dy dx is we divide both sides by secant tangent. So we can, just multiply by their reciprocals and end up with cosine y cotangent, because it was tangent over here, cosine y cotangent y. All right, so, but then what are those things? The y is inverse secant, so I end up with cosine of inverse secant times cotangent of inverse secant of x. All right, so now I'm going to have one triangle that handles both of these things, because they both have inverse secant. So I can make one triangle in which the theta is the inverse secant of x. Therefore, secant theta equals x. So that's, I already put it as x over 1, I guess. So then, let's see, secant is 1 over cosine. Cosine is adjacent over hypotenuse. So secant must be hypotenuse over adjacent. All right, so that means our hypotenuse is the x, and our theta is the 1. And then we can do our Pythagoras theorem and get square root 1 minus x squared over here. Okay, so now I need two different things. I need the cosine of this angle, and I need the cotangent of this angle. I need to multiply them. So the cosine of theta is adjacent over hypotenuse. So that's 1 over x. And the cotangent of theta is the cotangent is adjacent over opposite, right? Opposite over adjacent, adjacent over opposite. Yep, that's right. Okay, so our adjacent side is 1, and our opposite side is square root 1 minus x squared. Okay, so our dy dx is the product of these two things. It's 1 over x times 1 over square root 1 minus x squared. Right? So taking these two things together, we get that. Okay, so that we can simplify to 1 over x square root 1 minus x squared. All right, so what about the absolute value? So the absolute value is kind of a little bit of a trick. And so what it really revolves around is that in all of this stuff that we've done, we've always assumed that the x is positive. So when I draw this triangle, the triangle has a positive distance, a positive length. All right. So that so we've never dealt with x being negative. Now in all our other derivatives, that didn't matter because the x ended up being squared anyway. So the sign of the x was actually irrelevant on all of them. This is the first one where the sign SIGN of the x becomes relevant. Yeah, hang on 1 second. I had the Desmos all set up on my iPhone, forgetting that my iPhone is what I'm using to record the video. So having the Desmos set up there does not help. But we'll get Desmos. So what we're going to do is we're going to look at a graph of inverse secant. So to get a handle on what this x should be. So because you can do sort of a similar analysis. If you actually look at the book's analysis, they do something quite different that's interesting using trigonometric identities. This is the way it was first shown to me, and I liked it, so I want to stick with it. But then, so what happens when the x is negative? The triangle basically doesn't apply anymore. So this isn't really any kind of formal proof, but if we look at a graph of inverse secant x, and I wanted Desmos because to get a graph of inverse secant on your TI is a little bit tricky. Oh, there it is. All right. So what you can see is, and this is an interesting example of a function that is always increasing. It's always increasing, even though there's, it never gets higher than whatever number is here. We could figure that out, but it's inverse secant of whatever that is. I suppose that's 1. Inverse secant of 1 is probably like pi. All right, I won't think about it. It's probably pi. Yeah, that's pi right there. 123.14 pi. Yeah, and then for inverse secant, you cannot do the inverse secant of numbers between -1 and 1, because when you do 1 over that value, you're going to get a number that's outside of the range of sine and cosine. So, well, we could think about this graph. I didn't think about it ahead of time. It's pretty interesting. We have to think about that. I think I'll think about this for the rest of the day. It's pretty cool. It's got this horizontal asymptote at pi over 2. It's a pretty interesting graph. Anyway, all I really wanted to observe is this graph is always increasing. Therefore, right from here to here, it's not the domain of the function. So this graph is increasing on its domain. So wherever we are in the domain of the function, the graph is increasing. That means that the derivative is always positive, but this x is sometimes negative. So absolute value, Bajwenga. All right, that's not really a proof of why that is. Your book has something a little bit more thorough, but it's not worth our time today. So there you go. There's that derivative. And then I will just say about the inverse cosecant that it goes the same way. You don't have to do that one. This is a good one to do as an exercise. It's a really good exercise. I'm not assigning it, but if you want some practice, that's what it is. So now I've shown where all these results come from. It's something you don't critically need, but it's really good to sort of just look down that road and see what's down it. So the next thing I'm going to do is start talking about how we actually do some problems with it.